Well, thank you to the organizers for this opportunity, and thank you for having this program and me as a part of it. I wanted to start by saying it's my first time in the UK after Brexit. So, congratulations on getting back your independence. Somehow, in the last 6 days, we celebrated Canada getting its independence.
You're being recorded, by the way.
Going back to the Newton Institute, getting funding, renewed after that. No, Canada and the US, so somehow so many countries celebrating getting independence from the UK.
Don't you think it's interesting that Trump's visiting Poland?
Well, it's like the only country where Trump fits in as a moderate.
So should we celebrate in Europe that we are finally independent of UK?
Yeah, okay. So that was my little comment on that. So I want to tell you what my objective here is. My objective is perhaps not surprising given the title of my talk. So I want to establish a relation between, again, that's not very surprising, on one hand, type theories, and on the other hand, that's really not surprising, higher categories.
Presumably not the empty relation.
Sorry?
Presumably not the empty relation.
Yeah, not the. I would really like. How should I say, an interesting relation. And before I tell you how I'm going to establish it, I hope I will establish it. I'll tell you why I want to establish it. So, what we've seen so far in homotopy type theory, or univariant type theory, depending on how you want to call it, is that it is a very convenient language for synthetic homotopy theory. And what that means is we can prove theorems about homotopy theory in type theory and have them formalized, but they immediately become theorems about all homotopical settings in which we can interpret those theorems. So whenever someone proves Blaker's-Massey theorem in HoTT, it becomes a theorem about all possible models. And this is somehow very interesting, and we would like to have more and more models of HoTT so that this theorem becomes a theorem in as many models as possible. So somehow Andy Pitts was telling in his talk that he wants the world's simplest model of the univariance axiom. Now, I want the world's most complicated model of the univariance axiom. I want to see how many weird twisted settings this axiom can hold. Yeah. That's not all. So there's one way in which type theory, formal methods, can influence mathematics.
I mean, of course, there may be a depressing possibility that the world's simplest one is the same as the most complicated.
Well, I mean, for you, the simplest starts with, well, let's take a topos and then, so, I don't know how, I mean,
yes,
I think the definition of the simplest is also relative.
in the eye of the beholder.
So this is a way in which formal methods or type theory can influence mathematics. But I went to Jeremy's big proof and education session, and Jeremy said, well, ask not only how formal methods can help mathematics, ask how mathematics can help formal methods. That sounds familiar to something that I heard before, but yeah, it also goes the other way around. So Mike Schumann has a very nice paper about splitting idempotence in HoTT. And the paper arose from, well, actually, there are idempotents that you cannot split. But this is a very natural question to ask whether or not you're a homotopy theorist. You just ask a very simple question about a foundational system. And the way Schumann comes up with his examples of an idempotent that you cannot split and a coherence condition that you need to put an idempotent so that you can split it, well, these are essentially translated from Lurie, and his examples coming from higher-categorical. So the way I see this whole program is, well, we've seen examples of going back and forth between those two settings, and we saw that we can translate things by hand, but I'd like to have one master theorem that just covers everything immediately, rather than reprove every single little thing one by one. So that's my motivation for studying this. Now, if you've ever said in a boring talk that you don't understand anything in, you wish like the speaker at least define some basic notions so that you can have a slight idea of what they are saying. I apologize if you feel this way in this talk, but I'll define something simple so that I can give you a sense that I actually did some math here and not only talked about slogans. I'm going to define an infinity category for you and kind of tell you why this is a good idea. So this story starts with my favorite category, which is the simplest category. I think most of the HoTT community moved away from this category because somehow the model is not as constructive as you'd like. But it's a category that has objects and morphisms, like most categories do. It's actually an empty set of categories that don't. And so the objects are things that look like this. So these are just linear orders with n plus 1 elements in them, and then the maps are monotone maps. And when you take this category and then you take 3 sheaves on it, then you're going to get my favorite category, which is the category of simplicial sets. It's defined as a category of contravariant. So then when you look at it, an element x in here looks somewhat like this. X0, x1, x2, corresponding to each of the orders here. And now if you count functions from 0, so 0 has just one element, 0, to 1, there will be 2 functions. Either you choose 0 or you choose 1. So when I take a contravariant function, I'm going to get 2 functions going this way. And there will be 1 function going this way. Here I'm going to get 3 functions. And okay, this is as good as my drawing skills get. So I'm going to write 3 dots here. The next one will have even more arrows. So there are more functions, but if I just count subjective functions in one direction and injective functions in the other, I will be able to generate all of them by composition. And the way I think about the gadget like that is that these are points of some space, these are intervals in that space, and these are triangles in that space. And so what these 2 maps do for me is they give me 2 endpoints of an interval. So every interval is a directed interval, so it has a beginning and an end. And this thing lets me consider a point as a degenerate interval. Similarly, when I have a triangle, I can have 3 sides of the triangle, 1, 2, 3, and these correspond to the 3 maps here. I can also take my interval and regard it as a degenerate triangle. Either these 2 are the same or these 2 are the same. Now, this thing was studied in algebraic topology for many, many years, but it took several people, but I think most notably Joyal, to recognize that this diagram is not only a beginning of a somehow simplicial complex, but also the beginning of a diagram that you would draw if you define a category. Because a category has objects, it has morphisms, and it has composable pairs. And you get all the same maps that you would get here. So every object, well, every morphism has domain and codomain. Every object has its identity arrow. If you have a composable pair of morphisms, you can get the first one, the second one, or the composite. And if you want to take a morphism and get a composable pair out of it, you can stack the identity either at the beginning or at the end of it. So this is the key insight that makes the whole theory of infinity categories interesting or useful. So what's an infinity category now? Well, you can just take this intuition and formalize it. And I don't know how to use these boards, so I think I'm going to give up. Okay, so we can formalize this intuition by saying that there's a functor, I'm going to call it n, going from the category of categories to simplicial sets. And what this functor does for you is it sends a category C to a functor like that, whose n simplices are, let's say, functors from, this is n composable arrows to C. So in fact, when you take n equal to 0, 1, and 2, you're going to get those three things. Okay, so that was my little intro to that. But now I want to define an infinity category. And in order to define an infinity category, we need to see what the key property of this thing is. That is very complicated with these boards. So, okay, now that you can see the difference, I'm going to find out. I'm really lost. I spent the next 5 minutes thinking how to arrange it.
You can push the top one all the way through to the floor, no?
You could do if you wanted to.
I'm not comfortable with that yet. Maybe later. Okay. So I can have my n simplex, which is just the representable, represented by n. So I think about this guy as just a combinatorial n simplex. So it is what it is. And I have another one of those, except I remove some stuff from it. So this thing is obtained by taking one of those guys and removing the interior and the face opposite to the ith vertex. So if I take my I equal to 1 and my n equal to 2, this is what it's going to look like. So this is removing the interior and removing the face opposite to the ith vertex. So this is 0, 1, and 2, and this is the ugliest 0 in history. Okay, there we go. Then I remove the face opposite to that. Now there's a canonical inclusion here, and I can say that something is a nerfable category if, and only if, for every map like that, there exists a unique left here for all n's and for all 0 less than I, for all 0 less than I less than n. So what that means is whenever I give you a composable pair of maps, you can compose them. A fairly good requirement if you're doing category theory. Now, how do you define? So this is the defining property of one category inside of simplicial sets. Now, how do you define infinity categories? Well, you just remove this thing. That's it. So now I'm going to say an infinity category is a simplicial set, C now, such that this holds. I take I, n, embed it into this thing, and take C over here. Now there just exists a thing like that. And that holds for all n and for all 0 less than I less than n. Okay. Now I'm going to take this board all the way down and put this board. Okay. I guess that was way too aggressive. Okay. So that's it. So that's what an infinity category is. Now you should ask, why would I care? And here's the reason. Here's the principle. Category theory lifts to higher category theory. And what I mean by that is whatever interesting theorem you can come up with categories, you can come up with the analogous theorem for infinity categories. And since in Calc you can prove definitions, let's say that we're going to prove a principle. And proof is, well, read Royale and Lurid. That's my proof of this fact. I mean, every single interesting theorem that you can come up with in category theory, I can find you a corresponding theorem for infinity categories, or almost every, because some things are just not, are just stated by accident in category theory. But in particular, you can come up with notions such as finite limits, or finite. It's getting ahead of us. So, things like limits, slices, adjoints, monads, and so on and so forth. Okay, so here are my two questions. Question number one is how to relate or how to produce infinity categories from type theory. My question should have a question mark. And second, what are the properties of the resulting infinity categories? So these are the two things I would like to know. And I don't know why, but I'm using this board way faster than I'm using the other one, and this one is so much easier to use, which is just like bad planning, I guess. But okay, so let me tell you how to answer these two questions, because that's what this talk is about. So I'm going to start with a category of type theories, and my type theories are only dependent type theories. I don't believe in non-dependent types, which is a weird thing to say, but I'll say it anyway. But any type theory that I'm going to consider will have identity types. Now you can ask, what the hell is a type theory? Or what is a category of type theories? Well, I like to think of type theories as syntactic objects. So this is a bunch of it's like syntax, the types and terms and so on. But if you're more semantically minded, you can think of C systems, contextual categories, categories with attributes, categories with families, categories with benefits. What else is there? Type categories, comprehension categories, whatever you choose to think about. And when you have such a thing and it has the identity types, then you can define an underlying category with weak equivalences. So that would be a pair CW, where C is a category and W is a wide subcategory. So what that means is that it's a subcategory that contains all identity maps. In other words, it's just a class of maps close under composition and containing all identities.
Right, just a comment really rather than a question, just to slow you down slightly. So, I mean, were I doing ordinary first order predicate calculus or something like that, nobody I think would think twice if I said, and I'm only ever going to consider, theories in first order logic with equality. Right. Some people don't, but most people do. And there wouldn't be any question about what I meant about that. But here there really is, right, because it's not like there's fixed in stone one notion of what identity type means. I mean, yeah, Martin Lerth gave a particular definition, but there are other definitions, some of them are equivalent to his, some aren't.
Right.
So I don't know what you think about that.
What I think
so
about,
in other words, what's on the left-hand side there is a bit kind of fuzzy in a way.
right, so what I think about, well, I don't think it matters what I think, but
Nor me neither.
but maybe more importantly, the answer is I'm taking identity type as Martin
Martin.
defined it,
Okay,
regardless of what I think or how I feel.
Okay.
Like this is what it is.
okay.
Somehow, yeah.
So REFL, J, computation
Like,
rule for that.
good old stuff, yeah.
Yeah.
Okay. And so Vladimir defined weak equivalences, and if you want to define what a weak equivalence is, you only need really the identity type, because you don't like you would need sigma type if you want to define it internally, but if you're just defining external property of being a weak equivalence, you really only need the identity type. And from here, I have a functor to my infinity categories. I'm going to denote them cat infinity, which is a subset or subcategory of simplicial sets, which consists of those nice rings that have this property right here. Okay, and this functor is called HoInfinity. So this is a very simple functor, despite maybe the fact that there's very little here and there's somehow a lot here. And how do you produce one from another? Well, what you can do is you can take your. So I want to tell you what to do here, because you know what to do here. Just like you just take your your types as your context as objects and your terms as morphisms, and that's it. But this one may be slightly more interesting. So you take your category C and you take its nerf exactly as I defined over there. Now, this is great, but that only sees like one categorical part. It doesn't see any weak equivalences. So what you're going to do is you're going to take the disjoint union of all weak equivalences, and you're going to see them exactly inside of here as one simplices. So we're going to glue in a bunch of inverses for these things. Weak equivalences are things that ought to be invertible but maybe weren't, and we're going to correct it. We're going to make things right here. Making things right, speaking of Brexit and Trump. Boom. Okay. So then you're going to take a push out of this, and I still haven't told you what that is, so let me do that. E1 is just the nerf of the contractible groupoid on two maps. Or two objects, sorry. So it has two morphisms going like that, and it obviously has an inclusion from just a single morphism, and this is doing exactly this thing. It takes your category C and it glues in all the inverses, but in an infinity categorical way. Now, the problem with that is that this may not be a quasi-category, so we're going to do what's called a category replacement. And I'm not going to talk much about that, but you can just do it, and it's fine. And you're going to get a quasi-category. And this quasi-category is the quasi-category that I want to study. So if I call this thing the classifying category of a type theory, then I want to study the functor CL infinity, which I defined as the composite of those two. So it's HoInfinity composed with CL. Okay, awesome. Everything is going great. So we're back to the difficult board. So this next part may be a bit incomprehensible. Okay, so let me state a theorem that somehow summarizes what you can say. So I can consider different kinds of type theories here. So I can take identity type, and it actually doesn't cost me anything to add sigma types as well. And from that, I can take this functor CL infinity, and instead of landing in general infinity categories, somehow I end in infinity categories with finite limits. So these guys have finite limits. And if that sounds familiar, it should, because Clarenbeau and Dibier proved an analogous theorem for extensional Martin left type theory. If you take extensional identity types and sigma types, you're going to end up in categories with finite limits. Now we're taking intentional type theory, and somehow everything lives. I can also add to this type theory, because this is not, I mean, if I ask you what your favorite dependent type theory is, it's not going to be this one. Like, I understand it. So I can add pi types with functional extensionality. And if I take the same functor, my target will actually be locally Cartesian closed infinity categories. And that again mirrors the analogous theorem we had for extensional type theory. This is a modeling of extensional type theory in locally Cartesian closed categories, but now our categories are locally Cartesian closed infinity categories. And finally, you can say, okay, what's going to happen if I take something like HoTT? Well, the answer is what you should get is elementary infinity toposes. And this is not yet clear for several reasons. Actually, there are 3 reasons why it's not clear.
One is because it's sort of just under the blackboard.
Well, this is the best we can do. This is the progress that I wanted to report on in this talk. Okay, so there are 3 things that are not clear. The first thing is, what is this? The second thing is, what is this? And once you fix those, what is this? But other than that, it's perfectly fine. Now I want to point out one thing, that it took, I think, 5 papers to even show that these functors have the right codomains. Like, it's not an easy exercise. It's not, yeah, the details need to be worked out. Go ahead, work them out. Like, it took a bit of work. As someone would say, believe me. Anyway, but that's a theorem. Now there's a conjecture, which is, or maybe, oh yeah, you can totally do it. So if you look at the case of extensional type theory, where these identity types admit the reflection rule, like these 2 arrows are known to be biequivalences of 2 categories. And the conjecture is that all CL infinities are equivalences of infinity. So that's a very difficult statement to prove, at least for me. But I tried anyway. But again, going back to my initial motivation, what that would mean is that exactly if these 2 are equivalent, we have a way of translating theorems from here to theorems about those guys, and similarly translating properties of each of these into principles that you can add to your type theory. Okay.
Question?
Yes.
The things on the left, they are models of essential algebraic theories. So you're not thinking of them as these models categories as infinity categories just because they're one category. You think adding an extra structure?
Well, so the next thing. So my next sentence, like literally my next sentence was, so far I only told you what are objects and morphisms here, but if I want an equivalence of infinity categories, I need to tell you what is the infinity category structure on that.
But
So
that's easy, because you see what it is on that side.
No, right.
I'm only half joking, because that's kind of what happens in classical categorical logic, in a sense, that morphisms, between theories turn out to be what you want them to be in order to make a nice bijection with certain kinds of structured categories.
Right. Yeah, so that obviously would be a perfectly good answer, but in that case, really there's not much to prove. And like it's not gonna be that hard to do it. So obviously, what we want is more.
Well, I mean, there is something to prove, because I mean, I guess have you proved that everything on the right hand side is is equivalent to something coming from the left-hand side. That would be the first thing to have to prove.
So, well, I'll say what I proved at the end.
Okay.
But I kind of want to answer the main question. The work of Joyan and Clory tells us what maps here and the infinity categories of these things are. But what the hell are these things? These are just one category. We don't want to compare one categories with infinity categories, like apples and whatever, trumps. So we would like to understand what is the notion of a weak equivalence here. And as already mentioned, we know what morphisms here are. So when is such a thing a weak equivalence? So I guess there's more to say because I still haven't really defined those as infinity categories. Okay, so I want to know, and I'm going to think syntactically. So I have two type series, T and S, and I have a translation between them. So if you think in terms of C systems or something, it's just a map of models of an essentially algebraic theory. And I want to know when such a gadget is a weak equivalence. Now, a homotopy theorist would say, look, well, these are both categories with weak equivalences, because you can just view them in this way. So we can ask, so a homotopy theorist would say, homotopy theorist tells you that when I take a homotopy category, I invert weak equivalences in one categorical way, how F is an equivalence. So that's great. That's great. But a logician maybe, or the type theorists, would say, well, when are two theories the same? One way of saying that would be something like by interpretability. So I can somehow have maps back and forth, and I can interpret one theory in the other, and so on and so forth.
Right,
But
there are logicians, and then there are categorical logicians who are even better. Right, and what they'd say, and which I think you really should be thinking about, is it's got nothing to do with some kind of function between that theory in the sense of types going to types and terms going to terms. It should be that you're looking at something where F is a model of T in CL infinity of S. Right?
So I'm not going to talk to those guys. I'm not going to ask those guys.
But that's the right notion of morphism. That's the right notion of morphism. A theory of T, a model of T in the classifier of S is a good notion of morphism.
No,
T to S.
I agree, but I think this is stricter.
Even if you have an interpretation which is rather strong in your sense, the fact that it's an equivalence, it may well be that the thing going back the other way is a much weaker kind of thing than actually being able to interpret the sorts that you started with. They're probably going to come out to be some defined thing.
So the
that's my two P's with.
no, I think we to some extent agree, but given the current state of our knowledge about these things, I think that would be very not,
difficult.
not easy.
I can easily see that.
But so by interpretability is only one option, going back and forth and so on. But we don't necessarily want to assume that an inverse exists. So another notion that would come to mind is conservativity. Conservativity. Okay. There's something wrong here. There we go.
Trying to write the word liberal.
Conservativity. Now we somehow want both at the same time. We just don't want to say. We just don't want one of those notions but not the other. So the best solution would be this. Now this is not a mathematically precise notion. I was told. So the way I would define
Cancelling the 2 on the top and the bottom, that means it's interpretability plus half of conservativity.
Yeah, okay. So what this would mean to me, independent type theory, would be that you have two properties. Weak type lifting. So, okay, so I have T, I have S, and I start with a context here. I have my map F. I start with a context here, and so I have for this and a type A in this context that exists. Oh, gamma A bar type together with a weak equivalence. So I'm going to say W from A to F of A bar. Okay. So this is one way of defining. Whatever I can define here, I can lift it and define also in here. So that's one part of it, and then the other part that I'm not going to tell you exactly because I have 10 seconds left, and I think I'm going over time, by the way, will be something like weak term lifting. And what that means is the analogous property, but now you start with a context and a type, and a term downstairs, and you can lift it to a term together with a path. So somehow you can do the exact same thing that you do in homotopy theory, where you can invert your map on homotopy groups locally, but not globally. So I'll leave it as an exercise for you to figure out what this definition is. But okay, so we have two answers to this question, and I think what I okay, that was not good. Okay, so here's a theorem. These two notions agree. So something is a homotopy theorist and a logician are talking about the exact same thing, it's just they are using different languages. And to me, this is like the whole fun of doing homotopy type theory. We're just discovering over and over again that we've been talking about this same thing in two different languages for many, many years. So before I finish, let me actually tell you what is the progress, because somehow this talk is about telling you what is the progress here. So let's say the Lex infinity part. So this lower thing, I think, is an equivalence. We can, oh, sorry, I should have said one more thing. Because what that does is it establishes things like sigma id inside of categories with weak equivalence, because I just equipped it with this notion. But now I can hit it with co-infinity, and I can get an infinity category out of a thing like that. And this defines for me infinity categories on the left hand side. So as far as the bottom row is concerned, we know everything. That's what we're writing it up, but we know everything there is to know. This functor really is an equivalence of infinity categories. As far as the LCC row is concerned, we have the assignment on objects. In the opposite direction, if C is presentable, and finally, there are tentative definitions of elementary infinity toposes and HoTT, and there are partial assignments on objects in the opposite direction. Now I'm in a very weird situation because I wanted to mention a result of yours, but you weren't here, so I was like, okay, I'm not going to mention it, but now you're here, so maybe I should mention it. Okay, so
I would have liked to come, but I only found out now that your talk is anyway.
I didn't like
Maybe
it
I can see
either,
the
so yeah. Okay, so now you can ask, okay, are there any interesting examples of this notion? And yes, so if you look at, so I can take type theory, and because, okay, I defined some weird notion that I call bi-interpretability plus conservativity divided by 2. So you can ask, do you have any examples of bi-interpretability plus conservativity divided by 2? And my answer is yes. So if I take type theory with pi sigma identity types and functional extensionality and TYP, I can interpret it in type theory for extensional type theory. So I have reflection. And it's a theorem of Martin Hoffman that, in fact, he didn't prove it exactly in this language, but if you look at the proof long enough, you see that this is an example of this notion. Is this plus this divided by 2. Okay, so this is how far along we are, and the goal of the whole thing is to finally understand the whole picture and see that a lot of results that we proved in HoTT by hand are really instances of this general master theorem. Okay, so I think I'm done. I'm out of time by like 5 minutes, and I had nothing to say, so I'll shut up.
I have a question, but I'm just seeing if anybody else wants to say anything first. Okay, I have a question. So,
That was encouraging.
I'm afraid higher infinity is just a bit too much for me. So, haven't you got a simpler way of describing it? What I'm thinking is not just because I'm old and tired, but you know, one thing you might want to do with something like this is use the left-hand side as an internal language for the right-hand side, because you want to carry out various constructions that would be more conspicuously described using type theory than they would be by, say, using model categories or whatever, blah, blah, blah. But, you know, that does require, doesn't it, having a rather simpler way of saying how CL infinity zaps your theory into its classifier, as it were. So is this a more direct way of building your Lex quasi category out of an sigma theory, kind of more directly?
Well, so the indirectness in this approach is this five-element replacement.
Yeah, because everything else is okay. I can understand weak equivalencies and push-out's not too bad, but then you did five-element replacement. Bloody you know.
And I mean, just to be perfectly clear, this five-element replacement that I didn't quite spend much time talking about is why this is difficult.
Yeah.
Like, that's the only difficulty in the whole theorem.
So if you could avoid it, it would be really good.
Yes. So the way this part is proven is by actually finding an explicit construction. So this is Shmuel's quasi-category of frames construction, which, as long as you have a bit more structure than just weak equivalence, you need essentially vibrations in your category, then you can describe it more explicitly. It's still not, it's not, you know, your objects won't be just types, but it's something you can work with.
And where do I see that? Sorry,
It's Shmuel to models for the homotopy theory of the co-complete homotopy theories. I can, yeah.
Yeah. Give me a reference. I'd like that. Any other questions?
Maybe now that you mentioned it. So can you just like say what you are aiming at with the same arrow? With the same arrow. So what is the analog to T sub UIP, and what's the analog in T sub ETT in your work?
Sorry, say that again?
Okay, here you say T sub UIP arrow T sub ETT.
Yeah.
Okay, so now I'm asking what is the analog in your result or in your program of T sub UIP and what is the analog?
Oh, there's no analog. This is part of the whole thing. I mean, these are perfectly valid type theories, right? So this is just one arrow that is, to me, a non-trivial example of a weak equivalence, like a map that, if I consider these things on the left as categories, that would be only like a map. That's it, end of the story. But because we are equipping it with this higher categorical structure, now we have a good way of saying this is an equivalence. So we want to think of it as an invertible thing. So that was. There's no analog. This is just like one thing that's captured by this theory. And I think it's a good and convincing example that this is like we're not completely crazy here. Session chat is gone, so let me tell you.
Well, let me then ask you what I think you would have asked. Maybe. So what about the categorical logician's notion of a morphism? Can we relate that to this thing we now know is the same thing?
That's a good question. That's all I have to say about that.
Yeah.